Maddison. I look after network engineering at Work Online Communications, and hopefully, if I get a clicker soon, I'm going to be talking about ASPA. ASPA, not ASAP, which is a really easy typo to make in your slides. I'm sure it will show up at some stage. So a bunch of my slides got written for me by colleagues who have presented earlier today. So thanks everyone who was talking about routing security and root leaks. I'm not going to rehash all of that, and I'm also not going to rehash kind of 101, this is what the RPKI system is and this is how it operates. If you're interested in talking about that afterwards, then I'm more than happy to chat to people about it, but I think that there's been plenty of kind of basic intro to the RPKI today, so we're going to skip all of that. This, however, is one of those topics which, at a kind of high level, intuitive level, is fairly straightforward and gets detailed and complicated and down into the weeds pretty rapidly. So I'm more than happy to take questions as I'm talking. I'd much rather be able to answer people's questions as they come up rather than waiting for the end and discover that I've lost half the room because I've gone into details that people don't have the background for. With that said, this is exactly the same diagram that I think it was Amrish had in his slides earlier. The kind of, the typical anatomy of a root leak. And this is the problem that ASPA seeks to prevent, where you have a prefix being advertised downstream to a customer who then, for want of filtering and whatever, leaks it back out to another operator with whom they do not have a customer-provider relationship, and that prefix can wind up going all over the internet and attracting unwanted traffic flows, causing congestion, potentially be a tool in an attacker's arsenal in order to eavesdrop, etc., etc., etc. Bad things happen when this stuff happens. And as it stands at the moment, we don't really, as an industry, have a good solution to this. There's an RFC 7908, I think it is. Yeah, 7908. Concerns itself with defining what a root leak is. And it uses this phrase, intended scope, which is a bit nebulous. And this is why things start getting complicated, and it's why we don't have a good way of detecting this stuff at the moment. Because it matters whose intention you're talking about. There are at least four kind of parties involved in this. There's the owner of the prefix that the leaked path is announcing a route for. There's the downstream AS or ASs who are propagating it up to their transit providers. There's the upstream AS who's accepting it and propagating it onwards to their peers and other customers. And there's the routing police. There's, essentially us, the people who stand on stages and say what's right and what's wrong. And one of the things that you need to do before you kind of really tackle this problem in a structured way is define whose intention actually matters here. Who is it in this diagram that gets to say whether P should end up on the right-hand side of that diagram or not? We talk about this stuff amongst ourselves in a fairly loose fashion, but we kind of all have an intuition about it, I think. I think most of us have an intuition about it. And that is that an announcement should be propagated essentially when either your left neighbor or your right neighbor is paying you to do so. If you have a downstream customer, they're kind of paying for two different things, at least from the perspective of a transit provider. You're being paid to accept announcements from your customer and have those propagate to other operators in such a way that the whole network hears, the whole of the internet hears about them. And conversely, in the other direction, you are being paid to provide reachability information so that their traffic outbound can in turn reach the whole of the internet. And it's that it's that kind of symmetric relationship that exists between customers and providers that can make this a little complicated. I would have put a citation in for the value-free model, but I wasn't actually that sure about which citation to use. Is it Kaida? Amrish, you probably know the answer to this. Was it Kaida that published the value-free model? Yeah? Was it? It was those guys. Okay. I will, when I put those on the internet, I'll put a reference there. The value-free model essentially describes that. It describes this kind of this abstract idea that we have about the topology of the internet, where prefixes should only go up the kind of chain of customer to provider relationships and then back down again once. Once they've entered a valley, they should no longer come out of that valley. I.e., where are we? This violates the valley-free principle. As you can see here, there's a valley between AS1, AS3, and AS2. An announcement has propagated down and then back up two sides of a valley, and this is what's prohibited by that model. And this ends up describing, at least at a fairly high level, the topology of the internet pretty well, as long as you get your definitions right. And so what we're trying to do here is we're trying to find a mechanism that is able to encode somehow enough information so that networks that are removed from the originator of the prefix or any of their peers, or where a leak's going on or maybe going on, is able to answer these two questions. Has the downstream network, has the network that appears on the right side of this, of some AS in the path, authorized that transit network to propagate announcements upstream? Or conversely, has the left neighbor authorized the transit to kind of essentially send the whole default zone down towards them? Are they a downstream customer? And it turns out that the information that's necessary to describe this is actually fairly straightforward. The algorithm to apply to that information gets a little hairy, and I'm not going to go too far into those weeds, hopefully. So the way that this is being thought about at the IETF, and this proposal called ASPA, has been around for a number of years now, and was kind of arrived at separately by a bunch of different people who kind of came up with different terminology for the same solution. And it's fairly well matured in terms of the actual protocol specification. And I'll talk a bit about at the end about where things stand in the standardization process and the implementation process. But it turns out that it's enough for a network to make available the set of providers that it considers authorized transits. Now, it's important to understand that by transits in this context, we're talking about any AS number that can show up as transit between two other ASs in the AS path. Now, usually that will be a kind of traditional IP transit provider, probably most people are used to dealing with. But it can include other things. It can include some sort of a sibling relationship where you have two autonomous systems that are essentially operated as a single network and exchange pretty much all of their routes between them. It can be scenarios where you've got bilateral purchase arrangements between two operators, maybe in different parts of the world. It can also, in some cases, include IXP root servers. In the case of root servers, mostly nowadays, the root server's AS number doesn't show up in the AS path, in which case this question becomes moot. We don't need to care about it because this is all about validating AS paths. There are still a small handful of IXP root servers that do put their AS number in the AS path, and those root servers would need to be considered transit providers and included in a set of provider ASs, just like your IP transit, your IP transit network or your sibling network would be. Now, just like every other, well, not quite every other, like most other RPKI-based technologies, this revolves around the use of a newly defined signed object, which is a blob of binary data which is signed using a CMS wrapper and published in one of the RPKI publication points for everybody else to go and retrieve and validate cryptographically. In this case, probably the single most important property of a signed object is a definition of who is responsible for signing the data. Who is the one that's making whatever assertion is being made in that object? In the case of ROAs, that's the prefix holder. In the case of BGP SEC certificates, for example, it's the AS number holder. In this case, it is the customer side of the relationship. The provider side of the relationship does not need to say anything about who their customers are, which is a really important property of this, because lots of, I mean, this is true for us, for example, lots of service agreements preclude providers from talking publicly about who their customers are. And so one of the really nice practical implications of this is it's only the customer that needs to talk about who their providers are. The providers can stay silent on the topic. And then similarly with the way that root origin validation works, there's an RP that's responsible for retrieving all of these objects, walking the tree, doing a bunch of crypto in order to check that all of the signatures over those objects are valid and that they are in fact signed by the right party, and then they're massaged a little bit in a way that I'll get to in a moment before being sent to BGP speaking routers. So the operational model is pretty familiar if you're familiar with origin validation. This is a slightly more formal definition of what these objects look like. There's a customer AS number and then a non-empty set of provider AS numbers. There's a version number just in case we ever need to do a backwards incompatible version change, which hopefully we will never need to do, because having thought about it in the context of ROAs, it turns out that that's actually really, really non-trivial and hopefully never needs to happen. The customer ASID is also trivial. It's just a 32-bit number. The interesting structure is the bit that talks about provider AS sets. Now, the first thing to notice is that this is non-empty. You can see that size between 1 and max means that it has to have at least one entry in it. The reason for this is because for, certainly initially and probably for a very, very long time thereafter, we're going to have an incomplete set of ASPA objects published by network operators out on the internet. And there needs to be some sort of a way of distinguishing between the case that no ASPA object has been issued by a particular customer AS versus an assertion by a customer AS that they have no transits. And those need to be readily distinguishable. And the way that we've chosen to do that is to simply prohibit empty sets, because that's where that ambiguity is introduced. In order to signal to other operators that I have no transits, I would create a provider AS set with one member, and that is 0. Because the BGP protocol standards prohibit the use of 0 as a identifier in an AS path, that necessarily means that cannot match against a route that you see out in the wild unless you have a quite nasty bug in your BGP implementation. And then the third thing to make note of is that this has probably been the most recent contentious subject. There was some disagreement about whether or not ASPA objects should be completely address family specific, whether you should publish one for IPv4 and one for IPv6, and they should just be ships in the night. That was how early versions of these documents were written. And my view, and hopefully the view I think that is going to end up winning out, is that that's not the common case. What I see personally is that the majority of operators have a mostly congruent topology between IPv4 and IPv6. The exceptions to that are far, far less numerous. They tend to be adjacencies with specific operators that have a very large v6 customer base and a medium-sized v4 customer base, without naming any names, or vastly different peering policies in one address family versus the other. But they're very much the exception rather than the rule. And so instead of having separate objects for v4 and v6, what we did instead was introduce this AFI limit field, which is optional, and if it's omitted, then it simply means this provider is my provider regardless of address family. This assertion is valid for v4 and v6 and hopefully nothing else after that. Question? Go.
Amrish, so I give it right, they read to the document and it says you can only create one ASPA object. Is that correct? Like a customer can only create one.
You can't prevent because of the way that the RPKI is organized, you can't prevent multiple objects from existing. So can I come back to that question in a second? I have a different slide that's a better time to talk about that.
It was like conflicting with the fact that you have to address
So that limitation is per customer AS per AFI anyway. So it's the tuple. But it applies in a different, so early versions of the drafts did say essentially what you're saying. Since this changed, it's been changed a little bit, so that does still apply, but it applies on the wire in the RTR protocol instead. But I will get to that, because for me, that's the biggest single thing that needs more text still in the draft. But we'll come back to it. But the semantics of the AFI limit are simply, if it is present, then what it means is that this particular provider is only my provider in this particular address family. So it allows people to express policies like, AS 65,000 is my upstream for v6, but he's a settlement-free peer or perhaps even a customer for v4. The lifetime that these things go through is a little complex. And part of the complexity is caused by what Amrish just hinted at in his question, about the fact that we've learned a few lessons from dealing with rowers at this point. And one of those is that it's important to avoid race conditions between different objects. It is perfectly possible for in fact it's frequently the case, that a rower for a prefix is published in a different place than a rower for its subprefix. And it's quite easy to construct race conditions where you get where you retrieve the super prefix but not the subprefix, rendering the subprefix invalid, or the reverse, which is less harmful but still problematic from a troubleshooting perspective. One of the explicit goals here was to try and avoid situations where more than one piece of data on the actual BGP speaker influenced the algorithm outcome for a particular path. So in the case of rows, it's frequently the case that for the same prefix you have multiple rows that all match that prefix and all need to be considered when arriving at a validation status. The way that that's avoided here is by having essentially kind of like BGP-like withdrawal semantics for the actual data that gets sent to the BGP speaker. It is unavoidable, because of the way that the RPKI publication system works, that it's possible to have multiple ASPA objects in the system with the same customer AS number. There's simply no way of defending against that from a protocol perspective. It is recommended to operators that there only be one. But there are situations where there need to be more than one. So, for example, if you are transferring address space between RIRs, there would need to be some sort of overlap in order to accommodate that transition. Where this guarantee happens is at the RP, the link in the processing chain that's responsible for doing the cryptographic validation and sending that data onwards to the router. This middle step essentially takes all of the ASPA objects that are created by customer AS, takes a union of all of their providers, and kind of trims them according to that AFI limit field if it's present in any of them. And that will result in either 0, 1, or 2 AFI PDUs, aka VAPs, which stands for Validated ASPA Payload. Those can be guaranteed as being atomic per address family. And that protects against that race condition. So the worst really that can happen is that you, by publishing multiple objects that don't agree with one another, the worst you can do to yourself here is making your policy a bit too permissive. But you can't shoot yourself in the head like you can with rowers. This is the meat of it, really. This is kind of how we go from this data about who are my upstream providers to some other network elsewhere in the internet observing an AS path and needing to make a decision about, is this a leak? Is this actually showing up here in contravention of someone's routing policy along the way? And this was the bit that I was really unsure about how much detail I should go into, because this is the bit where the intuition is straightforward. I think that pretty much everyone here has got some experience operating a BGP speaking network, has a feel in slightly hand-wavy terms for what's a route leak and what's not a route leak. It turns out trying to formalize that in language that can actually be implemented in code in BGP implementations is a little bit hair-raising. Although the recent versions of the draft have gotten a bit better. But so if I'm skating over too many details that are necessary, please ask questions. If you want me to go into more detail and get down into the weeds, I'm happy to do so, although that might be best out the front there rather than while I've got a microphone in my hand. Essentially, every path, in a similar sort of vein as to how origin validation works, the process is that a BGP update is received, each of the paths in that update is inspected, and the AS path is examined. The AS path is compared to the complete set of ASPA data that's present in the router's memory, that it's received using the RPKI to router protocol that I spoke about in that previous step. And there can be one of three outcomes. Either the path is valid, which means that you can think of this in a few different ways, but the way I like to think about it is every transit AS in that path, i.e. every AS number that has both a right neighbor and a left neighbor in the path, was authorized in an ASPA by one of them, by one of its neighbors, either in the upstream direction or in the downstream direction. And that applies to all of the transit ASs in the whole path. So you can be absolutely certain that this conforms to the policies of the intended routing policies of all the networks. Invalid is obviously the converse of that. It's you have enough information to say for sure that there has been a violation of at least one person's routing policy in propagating this prefix. It's entirely possible for a route to be leaked more than once. In fact, it's quite frequent, because when you get through the first set of filters and you leak and you kind of violate some rule that someone further upstream expects to always be true, chances are greater and greater that you end up sneaking through other route filters as well. So it's not necessarily the case that exactly one trans AS in the AS path has acted in violation of someone's routing policy. It's invalid as long as there is at least one. And The third state, which will for the foreseeable future be the massively most common one, is unknown. We simply don't know enough to make either of those other assertions either way. An the unknown state is not necessarily problematic. I mean, you can imagine a situation where everyone but a large transit operator somewhere out on the internet who has a lot of peering and a large customer cone, everyone else creates a bunch of ASPAs, but this one operator doesn't. That would have the effect of making a very large portion of the paths out in the default free zone unknown, because you're missing that one kind of key piece in the puzzle, meaning that you can assign the status of valid to very, very few paths. But it still means you have a huge amount of information about the topology in the rest of the internet, and the net result of that would be, although people in the immediate neighborhood of that one large operator might still be susceptible to single hop leaks, the rest of the internet would actually be very, very well protected. So having status unknown is expected and not problematic. It's simply there for want of a better phrase, frankly. The current verification draft, I personally think, does a not great job of explaining the verification algorithm. It is correct. I've looked quite thoroughly at it. I've written test code for it. A bunch of other people have. A bunch of people have implemented. I'm fairly well convinced that the procedure that's outlined in the current internet draft is correct. It also makes you want to lie down in a dark room after reading it. And I'm kind of hoping that we fix this before it gets published, but we might not do. And that's why I haven't copied and pasted the explanation in here, and I'm going to try and do that in prose rather than by talking people through internet drafts. The current version of the draft splits the algorithm into two different scenarios. And the first one is the kind of trivial one. It's referred to as the algorithm for upstream paths, and it's there to be applied to paths that you have received from non-transits. So that's, in the ordinary course of things, that's your customers, that's your peers, that's usually root servers at internet exchanges, anyone from whom you are not expecting them to send you their non-customer peer routes. And in that case, the algorithm becomes trivial, because you're expecting to find an unbroken chain of customer to provider relationships. As soon as that is violated, it means that one of your customers is advertising a prefix for one of their non-customers, which is a violation of that kind of implicit trust model. And that's, if the whole internet looked like this and we were just one big ladder of ever increasingly large transit operator with a shared customer cone, then we'd be done, and we'd have solved this problem years ago, because it's easy. The difficult one to articulate is the reverse. It's the algorithm that is applied to paths that you receive in the downstream direction, paths that you receive from a transit. And in this case, let me switch to this slide. In this case, you're expecting the propagation path to look something like this. There is an origin somewhere who advertises it to their transit and to their transit and to their transit, and so on and so forth, until at some point you encounter a non-customer to provider relationship. In this diagram, that's ASK. There will be maybe some settlement-free peering going on up there. There might be a sibling relationship at the apex of that cone. Various things could be going on there, and this is kind of what the whole validation algorithm is there to try and work out. And then at some stage it will start flowing back down again. As the receiver, your transit will get the path, and then your transit, and so on and so forth until it arrives at you. But you should expect that upward-facing cone shape. And essentially what the algorithm that's articulated in the current version of the draft says is that you can decide for sure that something is valid as long as there are no ASs between L and K. If they are either the same AS, so this is simply a shared, the origin and the receiver are in the same customer cone, L and K might be the same AS, in which case this is fine. If they are settlement-free peers, and neither one is in the other's set of authorized providers, that's also fine. But as soon as there is another AS in the middle there, call it ASM, as soon as M is there, M has leaked a route between K and L. And we know this because if there was a customer relationship between K and M, then that would form part of the upramp. And the upramp wouldn't terminate at K, it would terminate at M. Similarly, if they were a upstream provider of L, then the downramp wouldn't terminate at L, it would terminate at M. The only way that you can have an operator in the middle of these two halves of the diagram without it being without them being included either in the upramp or in the downramp is if a leak has been caused. Now that's the description of how things can be valid. Unfortunately, it only describes validity. If you are trying to tell the difference between invalidity and simply not having enough information, then you need to generalize this even further. Do I have a slide about that? No. And I kind of feel like this is the point at which I'm straying into too much detail for today, but I can talk about it if we have time, maybe. Should.
Hi, Ben. Is there any thought in describing this in a way that's such that if you were to receive a default route, if you see something that appears to be, as specified here, to be inappropriately advertised, but if you're going to follow that way for default route anyways, what would be the expected behavior difference that a service provider, that a provider may have? I think this is in part a bit more of a generalized question as well, but in looking at this, if I don't have an alternative path to that network, it may not matter that I've detected it as invalid.
Yeah. That applies to origin validation as well, right? I was actually going to ask you earlier when you were talking about origin validation at Akamai, do you guys not carry a default? Because it's less exciting if you've got a default, right?
It's, at least for us, and I'll respond slightly to that, which is that the goal is to suppress as many intentional invalids as feasible. Mm-hmm. Because with many things today, an RPKI unit is unknown. And back on slide 12, when we're talking about the ASPA, there's not really a not defined there either, right? Because I don't think that's possible here, because once you publish an object, then you're saying who should be visible, and that you're unlikely to end up in a situation where that relationship would be not found.
Yeah, so the equivalent of not found is this unknown status. And that arises when there are ASs in the AS path that haven't published information. You're right, once an AS has published an object, they are all in with that object. It's not partial information. I suppose where this is still useful in the kind of situation that you're describing is you can imagine a sub-prefix hijack with a spoofed AS path in order to try and circumvent origin validation. So you stick the victim's you stick the victim's AS number behind you in the AS path and deaggregate. You would be able to. It's quite likely as a receiving party that you've got the legitimate prefix, which is now shorter than the attacker's prefix. Yeah. Whether or not you receive a default in addition to those two prefixes, still in your interest to be able to detect the attack, which this would allow you to do, hopefully, as long as, other than in very, very specific unlikely topologies where you are in fact buying transit from your attacker. In almost all scenarios, you'd be able to detect that attack, and you wouldn't end up falling back to your default. You'd end up falling back to the correct, shorter route that you have in your table from elsewhere. Yeah? If you're following the default for that prefix anyway, then it's kind of not your job to fix this, it's your transit providers.
Yeah, and one of the things that we've observed is that many providers, especially smaller ones, they don't, even if they receive a full table from the provider, they quite often have portions of it that they'll either ignore or filter out at some point, and have the prefixes that just follow the default.
Yep.
And that's something which I'm seeing that increasing behavior of, because carrying a million routes in your, not only in your grid, where you're going to end up with 2 million or 3 million paths potentially, but then end up with a million entries in your fib, that ends up being quite problematic to a lot of this analysis.
Yeah.
So I was just kind of curious if you thought about that as part of this. This is a very difficult space, and I think one that needs a lot of input from people, especially people in interesting parts of the world, where these relationships are not always as clear. Where you have friendly backup transit that you need to, the super secret backup transit that you will never publicly admit that you have, but once you publish an object like this, will become invalid. And this is something I think is really going to be essential for the deployment of these types of technologies.
Yep, totally. Yeah, so the super secret backup transit is a problem for this. There's not really a way of getting around that. You've got to either tell people or not tell people. You can't simultaneously have told people and not told people. That's just not how cryptography works. I think that there are... So I don't think that this has the same degree of utility for everyone. I think that I think there are even applications of this to making sure that you are receiving a default from somewhere sane. Even the act of validating that your default came from the place where you expected it, this could potentially be useful in a way that ROV probably isn't really, other than in a very weird corner case. What we've observed, and that arrangement that you're describing where people will take a default plus maybe some sort of partial table from their transit and a bunch of peering routes, that's common in our customer base. It's very common in our customer base. And in general, people prioritize the fib slots for the prefixes where they're sending traffic. As a result, the utility vis-a-vis any particular prefix is actually quite likely to naturally be proportional to the amount of traffic that's flowing towards that prefix. You'll get the least use out of this for your least used prefixes, which is quite a nice property. It's not obvious to me how we do better than that, but I think that's already quite good, actually. Does anyone want me to? No, in fact, I don't have time. I'm going to skip over the details of how we go about determining whether something is invalid. I will be that way if anyone wants to hear those nuts and bolts. But it's kind of, it means what you think it means. It really does. Unfortunately, it's just not written that way. This is an unusual area because it's one where we really don't have good alternatives. There was noise at one stage back in the dawns of time about doing a kind of a transit via thing in IRR ordnums. Was that you, actually? No. But as it stands, that never really went anywhere, and as it stands at the moment, the ordnum object doesn't even have a way of expressing this idea of I've got this neighbor, and I expect this neighbor to announce my prefixes to all of these other neighbors. It's just not something that you can say in RPSL today, even if you wanted to, which I would argue you probably don't want to quite a lot. So IRR data is not on the table for solving this. Peer lock is a interesting, I don't even want to call it a technology, it's a methodology. Fair? It's a methodology for essentially doing this by hand. It essentially involves, Jared can speak a lot more authoritatively about this than I can, but it essentially involves exchanging a lot of email with a small number of trusted third parties in order to keep each other informed of what the topology should look like between your networks, and constructing a bunch of horrendously complicated ASPath regex filters to express that. And it seems to work. I have never spent my time doing that personally. I know people who have. Feel free.
Hi, Jared. The thing that I'll comment on, so there's two different ways. You can either filter your peers or you can filter your customers. And when I was doing the original BGP research stuff back in 2007, that led to what eventually got branded to be PeerLock. The intention was to ASPath filter your customers to not accept routes from them that had the ASs of your upstreams in them. You could also then take that and make it more complicated and build a list of, I shouldn't see these ASs from these networks. So if you're a larger provider in an area, you could do that as well. But it's kind of dependent upon trying to filter out some of that garbage routes from either one end or the other to go and make sure that things do the right thing. But filtering on the customer side, where if you're buying from, whatever Telia has rebranded itself to this month, if you know you're buying from them, you probably don't want to see an ASPath with that ASN, with $12.99 in, from your customers. And that becomes a much easier thing to do than writing a much more complex regex. Because you can say, these are my transits, and you can do that, and you don't have to publish that list yourself as a service provider, which is very helpful.
Thanks. Fundamentally, the principles are the same. It's how you arrive at that configuration. It's existing policy constructs that exist on implementations, and it's a lot of very manual work. And in the case of, it was NTT that did it first, I believe, and they only have the trivial case, because they're transit free. Doing PeerLock for this case would be very, very hard indeed. And then thirdly, I quite often hear BGP sec and ASPA being kind of lumped into the same category of being ASPath validation or ASPath verification. I mean, that's true, but they say totally different things about ASPaths. This is about taking an ASPath as given and comparing it to what you know about the routing policies of the people that show up in that path. Whereas BGP-sec is about taking an ASPath as an untrusted piece of input data and saying, but they are totally different. BGP-sec does not solve the problems that ASPA addresses. ASPA does not solve the problems that BGP-sec addresses. They are independently useful and totally complementary. So stop it. I've said most of these things already, and Amrish is going to kick me off the stage. But I think that I think he has some really nice properties. You don't have time, man. Sorry. I'd like to spend what little time I've got left just talking about this sort of stuff. The specification of the object profile, I think, is hopefully done. The verification draft needs a further revision. I'm hoping to make some changes to it during the course of next week at the IETF meeting. But it is currently in last call. It's nearing the end of its life as a draft, and I think that it's not unreasonable to expect that an RFC that the RFC should start being published maybe in the kind of last quarter of this year sort of time frame. So like the progress is good on the standardization front. The progress is also good in terms of the implementations, with one very glaring omission. Krill, RPKI client, Routinator, Ripster, StayRTR have all implemented or are in the process of implementing their parts of this puzzle. You can stand up a ASPA supporting RPKI infrastructure today using stable versions of code from most of these implementations, and it works perfectly well. It's fairly well tested. I've done interop stuff with most of them. It's good. Things on that side are happy. As far as BGP speakers go, there are only two that I'm aware of, one of which is OpenBGPD, which is the OpenBSD implementation, and then there's NIST's experimental Quagga fork hybrid thing, which I probably wouldn't even run in my lab. There is a lot of work to do from BGP implementations here. In particular, none of the commercial network operating system vendors have even indicated a timeline for support, let alone started shipping anything. So if you would like to be able to detect root leaks and you use any form of commercial BGP implementation, please go and tell the people that you buy it from, because the last thing we want is to have a rerun of origin validation where everything gets standardized and agreed upon, and then 10 years go by before anyone is in a position to actually run it in the field and find the bugs. And there's some impetus for this at the moment, and it's important that we keep up that momentum. And I'm done.
Thank you, Ben. I think we'll keep the questions for the coffee chat. Thank you. Next up is John Brown from Team Kimberly.